I'm Dr. Bill Cordua. I'm a geology professor associated with the University of Wisconsin River Falls. A lot of people ask me how I got started in geology. Well, when I was a kid, I loved picking up rocks and learning about them. That really got me started. A lot of people share this interest, and the first step to really enjoying and appreciating what you find is being able to identify it. And then the first step in identification is figuring out what minerals you have in a particular specimen. Minerals are the building blocks of rocks. If we take a typical rock like this granite collected from the Black Hills of South Dakota, the entire rock is a granite, but it's clearly made up of smaller items, including some type of feldspar, quartz, various kinds of mica, some black mineral, which is a tourmaline. So this rock is composed of 4 different types of minerals, and the identity of the rock itself depends on what those particular minerals are. So since minerals are the building blocks of rocks, that's why we start with mineral identification. There are over 4,000 minerals known on our planet. In reality, though, you only need to be able to recognize about 20 of them to start unlocking the secrets of the rocks that you're likely to find in gravel pits and stream valleys in our area. In order to identify these, you have to use some fairly simple tools and some pretty basic tests which are easy and fun to use for both adults and for kids. Here's my basic mineral identification kit. It has a little piece of unglazed porcelain called a streak plate. You can use the back of a bathroom tile if you want to, although these are pretty inexpensive to acquire. Have a little glass plate like this, some nails, just hardware store nails, a piece of copper, an old penny will usually work, a magnet, a bottle of very weak hydrochloric acid, and a magnifying glass. Even a fairly basic cheap one like this will increase your enjoyment of identifying rocks, but I like to use one that's a little bit better magnification and it gives me a little bit clearer images. If you're really going to enjoy rocks, so a magnifying glass is very important. You'll be surprised all the things you can see if you make your samples a little bit larger. To a geologist, minerals are naturally occurring, inorganic solids with a distinct chemical formula or composition. They also have a regular internal ordering of atoms called a crystalline structure. Some minerals have crystalline structures that are based on cubes, like this one. And notice in a crystalline structure, not only do you have atoms arranged in particular order, there's distinct spacing between each atoms that occurs in 3 dimensions. So here's one that's based on a cube, maybe like the mineral table salt or halite, or maybe like Wisconsin state mineral Galena. All have this basic kind of internal structure. Other minerals can be based on other types of shapes. Here's one. This is the mineral calcite, and it's based on the shape of a parallelogram. And this is composed of calcium, carbon, and oxygen atoms that are all arrayed in a particular pattern. So sometimes the pattern can be a little bit more complicated. Here's another crystalline solid. The atoms are arranged in very distinct layers to them, and these layers, if you can see it from the side view, are arranged in distinct hexagons. Every mineral has some sort of internal regular order, whether it be based on a rectangle or a cube or a hexagon, a parallelogram, or whatever. And this is very important to why minerals have certain physical properties that we use to test them. So now it's time to start testing minerals. Here we have a number of different minerals, and the first thing most people notice about them is that they have different colors. We have a pink one, a red one, a purple one, a brown one, and a clear one. But interestingly enough, these are all the same mineral. These are all quartz. And the differences in colors represent the differences in trace element impurities that have crept into these mineral structures. Impurities can creep into a mineral structure because there's so many open spaces. And these can trap elements like iron or manganese. You don't need many of those things entrapped here to have a large effect on a mineral's color. So color is actually a fairly lousy clue to use in identifying different minerals because it just depends on what trace elements impurities happen to be around when many of these minerals are forming. A better test for identifying minerals is called the streak test. The streak is nothing more than the color of the mineral's powder. And interestingly enough, making a powder of a mineral reduces the effect of the trace element impurities, and thus is a much more reliable guide to what the mineral is. It turns out that all these quartz specimens would have a white streak. There are a number of ways to make a streak. You could make a streak by simply taking the rock and pulverizing it with a hammer, but that would be pretty destructive as well as a lot of work. Another way to do it, though, is to use a plate like this. This is a piece of unglazed porcelain. We call this a streak plate. In order to do the test, simply take the rock sample and rub it across the streak plate surface and observe the color of the powder you have left behind. That's a streak. So you find that this relatively brassy mineral leaves a black streak. There's another handy light property called luster, and there are basically two different types of luster. One type of luster is called a metallic luster, and this is found in materials that either reflect or absorb virtually all the light that falls onto their surface. These are two metallic minerals, but they leave a dark streak on a streak plate. So little light can penetrate this that even in thin chips, like on the streak, the mineral does not lighten up. Most common minerals have the other type of luster, which is called non-metallic. Non-metallic minerals allows at least some light to penetrate through them. Some minerals, in fact, are completely transparent and you can see through them, but others are a little more grudging and let light only through on thin edges. Nevertheless, we class all these materials as non-metallic in their luster. Here's a group of non-metallic minerals. They can be a variety of colors, and some of them can be relatively dark, and some of them can look very nice and shiny like this one. But all of them will show light through on very thin edges, and that's the evidence that it's non-metallic in nature. Another basic test is a hardness test. In this case, hardness refers to the ease with which a material can be scratched. A German mineralogist named Friedrich Mohs developed a rather famous scale called Mohs Hardness Scale, which ranks from 1 to 10, with 1 being a very soft mineral that's easy to scratch with all kinds of items, and 10 being the hardest mineral, which can be scratched by virtually nothing else. Most people are familiar with 10 on the Mohs scale as being diamond. Number 1 is a mineral such as talc, which is soft enough to be scratched with your fingernail. You can buy little Mohs hardness kits that generally contain minerals from a hardness of 1 up to a hardness of 9, including maybe even a little streak plate to throw in with it. But you really don't have to expend the money to buy this. You can use a much simpler group of tools. It turns out that your fingernail has a hardness of 2.5 on the Mohs scale. A copper penny is just a little bit over 3. A glass plate is about 5.5, and that's also pretty close to the hardness of just a common steel nail. Your streak plate has a hardness of 6.5. So with these little tools, which you can carry around easily in your pocket and can obtain pretty inexpensively, you can do some pretty sophisticated testing of hardness of an unknown mineral. Let's determine the hardness of this mineral. We might first see that it's softer than glass. It won't leave a scratch on glass, so its hardness is less than 5.5. We can also see that a penny will scratch it rather easily. So I leave a scratch mark on this with a penny, so it's softer than 3. In fact, I can even scratch this mineral with my fingernail. So I've determined that this mineral has a hardness of less than 2.5 on the Mohs scale. Minerals this soft are not terribly common. In fact, this is the mineral gypsum, which has a hardness of 2 on Mohs scale. Here's another unknown mineral. I can't scratch it with a penny. It's too hard for that. But this mineral will not put a scratch on glass. So its hardness is somewhere between 3 and 5.5. I can double check that by taking this nail and find that I have no trouble making a scratch in it with this nail. So I've determined this mineral has a hardness of between 3 and 5.5 on the Mohs scale. We'll test one more mineral. This mineral cannot be scratched by a penny. It's harder than 3. On the other hand, this mineral will put a really nice scratch, on my glass plate here. So it must be harder than 5.5. In fact, this mineral is hard enough to scratch the streak plate. So its hardness is greater than 6. There aren't very many common minerals that are harder than 6, and this happens to be quartz with a hardness of 7 on the Mohs hardness scale. Another critical property is observing the way in which a mineral breaks. Minerals break in certain ways that really are reflective of the way that they are put together on the atomic scale. A mineral like this, such as halite for example, is likely to break in cubes as the stress is taken along the directions of weak bonds in the mineral structure. Some minerals just break along irregular planes, like this quartz. That means that the atomic bonds inside quartz have about the same hardness in all directions, so there's no preferred way in which quartz will break. This material is Muscovite mica, a mineral that cleaves so readily I can do it with my fingernails, and break this into individual little sheets along flat planes. I'm breaking these along planes of weak chemical bonds in this mineral structure. Here's another mineral. This is halite, or rock salt. And if I hit this with a hammer, it breaks along regular planes, forming little cubes. It doesn't matter how often I hit it or whether I'm very organized or not. This mineral will break along very flat planes that are controlled by the atomic breaks in the mineral structure. We call this property, where a mineral breaks along regular planes, mineral cleavage. And we could say halite has 3 directions of cleavage at 90-degree angles. Very often you'll see cleavage described as the number of directions and then the quality or the angles between them. But the most important observation is that a mineral breaks along cleavage or has a fracture. So having or lacking a cleavage is the important determining factor here which we need to observe. Many times this looks better if you have a magnifying glass, and you can see these flat little planes or breaks better when you look at them through a hand lens. Another mineral that breaks along regular planes is calcite. If you hit this with a hammer, it breaks into fragments that have parallelogram shapes. In other words, they intersect at an angle that's definitely not 90 degrees. There are a couple of other rather useful properties. Even though you don't use them very frequently, they can be very diagnostic in certain cases. One fairly common mineral is magnetite, which is a metallic mineral, lacks cleavage, but is strongly attracted to a magnet. It's the only common mineral that will be drawn up by a magnet easily. This mineral is often found as black sand in stream valleys, and if you collect some of this, you can have some real fun with it with a magnet. So see if I sprinkle some of this on a piece of paper, like that. Much of the black sand we see in river valleys is actually magnetite. And if you concentrate some of this, you can play around with it with a magnet, which I have under the piece of paper here. You can play all kinds of games with it. Geologists often use a solution of weak hydrochloric acid, so-called muriatic or brick cleaning acid, which you can buy in hardware stores, and dilute it down to 1 part in 10. This is something that children should not do. Do this only under adult supervision in an outdoor area. Once it's diluted down, it's relatively safe, but even though if you get a little bit on your fingers or other parts of your body or on your clothing, you want to flush that area out immediately with plenty of water. Household vinegar can also be used as a substitute, but it too can sting and do damage if it happens to get into your eyes. So you need to be rather careful with this. But if you use this with some respect, this material can do a whole lot to distinguish some very, very common minerals. One fairly common mineral that reacts with hydrochloric acid is calcite. Calcite is so reactive that if I put just a drop of weak hydrochloric acid on the mineral surface, it'll bubble vigorously, making little gas bubbles of carbon dioxide, looking a lot like soda pop when you've shaken a bottle. Once you use the acid, though, make sure that you wipe up any and wash the surface off so you won't get any on your fingers or other clothing. Another mineral that reacts to hydrochloric acid is dolomite. This mineral, though, needs to be powdered before you can get a reaction. So if you take a nail, and it's not that hard to do because dolomite's softer than a nail, so we're actually almost doing a hardness test here. And once we get enough powder to test, we can also put a little hydrochloric acid on it, and we'll get a weak bubbling that suggests that this mineral is much better held together chemically, but still will release carbon dioxide to the atmosphere when we grind it up a little bit. So let's look closely at some of the minerals that are very common in our neck of the woods, around here in River Falls, Wisconsin, in the western part of the state. Let's take a quick review of some of the common minerals in our area. One of the most common minerals people find is quartz. Mostly it's palely colored, it lacks cleavage, harder than glass, but it can be a variety of other colors sometimes. And a lot of people like to pick up Lake Superior agates, which is a fine-grained banded variety of quartz. That's a semi-precious stone. Another material we have around here, find fairly frequently, are cavities in limestone where you have a lot of sparkly or druzy quartz crystals that have partly filled some of the cavities. These are very attractive materials, and people like to use these for garden rocks. A couple of other minerals we have in abundance around here are the carbonate minerals calcite and dolomite. We encountered these earlier as being reactive to hydrochloric acid. Calcite fizzing right away, dolomite fizzing when you make a powder of it. They both possess a distinct mineral cleavage, breaking in parallelograms, are non-metallic and a bit softer than glass. We have a fair abundance of iron-rich minerals here, and these are the three most common ones. This is magnetite, this is a mineral called goethite, and this is hematite. Magnetite's easy to tell apart. It's the only one of the three that a hand magnet sticks to. Interestingly enough, these other minerals are not strongly magnetic, even though they have a lot of iron in them. The iron is bonded in the structure in a way that does not give a magnetic reaction. They do differ from each other from the streak plate. If you do a streak test on each of those, magnetite will give a black streak, and it's also fairly hard. Goethite will give a brown streak, and hematite will give a red streak. So in order to tell these iron oxide minerals apart, a streak plate is really a good friend. Another common material we have in rocks around here is feldspar. Feldspar is actually a group of minerals, but we'll lump them all together and call them feldspars. They're usually fairly light in color, they're just a bit harder than glass, and they break along regular planes, usually in two different directions that intersect at close to 90 degrees. Feldspars are a very common component of granites and other igneous rocks. This is a sample of Wisconsin red granite, and the red mineral in it that gives it its distinctive color is the mineral feldspar. It also has quartz and usually some forms of mica in it to round out the rock. Speaking of micas, they are some of the easiest minerals to identify. There are two general varieties of them. The lighter colored mica is called Muscovite. The darker colored one is called Biotite. Both are non-metallic. They break along regular planes, making them break into nice little sheets. Many times the grains in the rock are fairly small, as they are in this sample of granite. The little dark fragments you see are actually biotite crystals. But in order to see them very well, this is where your magnifying glass comes in handy. It's also possible using the magnifier to see the little cleavage faces on the feldspar grains. There's one other metallic mineral to note, and that's the mineral pyrite, which is iron sulfide, sometimes referred to as fool's gold. If you use the mineral properties, though, you'll never get this mixed up with real gold. First of all, it's brittle, not malleable like gold is. On the other hand, it also is harder than glass, and gold is fairly soft. And also, if you use a streak plate on it, the pyrite will give a nice black streak, and gold streak will be a very pale gold color. So really, there's no reason to mix up pyrite and fool's gold if you have a large enough specimen to test. A few moments ago, we saw our state rock, which is red granite. This is our official state mineral, which is Galena. Galena is a lead sulfide. It's easy to identify. First of all, it's metallic. It's very heavy, having lead in it as an essential material. It also breaks in cubes, so it has a well-developed mineral cleavage. That makes this a very fascinating mineral to have. This was mined for lead in the early 1800s through about the mid-1970s, and was very important in establishing Wisconsin's economy when we first became a state, and that's why it's our state mineral. It's fun going up and picking up a lot of unique and interesting rocks and minerals, cleaning them up and having them sit on your shelf. But it's even more fun to be able to identify what they are, and their identity is the key to unlocking the many stories they have to tell us about the history of our planet.